So here we have the map of the world, and let me point out this is Mauna Loa, and this is where Cape Grim. So Mauna Loa, Cape Grim, and we can see if we these are all these arrows are showing ocean circulation patterns, and they are showing essentially how wind is pushing the water in the direction it's going in. Oh, here's Long Beach right there. So wherever you see the arrows, that's the way the wind direction is coming from. So the wind that's hitting Hawaii is coming off this California coast. We have a lot of activity. So there could be higher than normal CO2 levels here at Mauna Loa. Higher CO2 concentration. Cape Grim, you see, let's check this out. This air that's moving across isn't really going over any populated area. So this area here tends to be a little bit lower than the concentration of CO2 at Mauna Loa. So yeah, the basic wind direction, we just described that. And what might explain it is, you have a populated area, closer to Mauna Loa. Okay, and that could give you that higher reading. Basic wind direction, I guess. So Mauna Loa, it is east to west. Cape Grim, it comes from the west and flows towards the east. So two different wind directions. That's why you always want to have two different, data points, or preferably more data points. But two is pretty good for the kind of research that needs to be done here. So here we see the trends, especially you can really see there was this high point around the 1940s, but you see an increase. It kind of travels, but then you have an increase again. These are really, for as far as temperature from instruments, this is really 1850 is where it really starts being accurate. But you just see over time, if you kind of average this whole graph out, you see this increase. And that's what you want to do, is go as far back in time as you can. And then of course we have the ice cores, okay, data that show warming in connection with CO2 that we had earlier in the slide packet. So here we have these peaks, the last few thousand years, never really topping 300. Now we're up above 400, about 405 parts per million. And this is a real problem. How is our global ecosystem going to respond to over 100 parts per million higher? And this, we also actually can go back to 700,000 years, which covers a huge part of human history. Remember, humans, we're pretty sure used to be humans about 150, 100. Now we think maybe 200. But definitely in this range is where humans have been in this general fluctuation up and down. And what's going to happen here? Huge question mark. And the thing is, can we do something about it? And the answer is yes, we know what to do. It's a factor of us doing it. And that's what you all need to do. And that's why I'm here helping to help you understand these issues, because this is going to affect all of us in future generations, how the earth is going to respond to that change. And here we can see, again, from ice core data, but also radiologic data, where they put actually sound waves down through the ice to measure the thickness, and with satellite, space-based satellites, and you can see that general trend of thickness of glaciers. But see, if you look at this data, if you don't know what you're doing, you might fixate on this level, which shows kind of up and down. You think, oh, it's really doing okay. Same thing right here. This is what a lot of people do. They're denialists of global warming. They'll cherry pick. Oh yeah, look. Oh, between what's this, 1968 and 1973, it was increasing. So they might throw that out. Well, yeah, it was increasing during those years, but if you look through all these years, you'll see a decrease. So you got to watch out for that kind of cherry pick. They'll always set up a specific date for you to look at. Methane, this is, global warming gas. Global warming gas, from livestock and energy production. And again, you can see an increase, and also follows that seasonal fluctuation, partly because of land mass being greater in the northern hemisphere. And nitrous oxide, also global warming gas, increasing over time. Not quite as much of an impact as CO2, but still something that has to be looked at. So here we have CFCs. These cause a thinning of our ozone layer. And it's pretty amazing. We see this increase up until the early 90s, and then we see a level off and a decrease. And the big difference was, this is when the Montreal Protocol was signed. You see right away it started to level out and then decrease. And we still see that decrease up until present day. So this shows, what it tells us is that the world, and this, I really want to emphasize this, the world can change. And we have to, and that's a happy thing, we have to be focused on that. We can get better. We can get together as a world. This is, remember, 197 countries. I think it's a couple different non-countries of principalities, but that's the whole world got together and said, we're going to do something about this. We're going to eliminate CFCs from manufacturing and move to less damaging chemicals. And they did. The world has done it. We've seen an improvement in the thickness of the ozone layer. He should be in his box. Yeah. So it tells us that the world can change. To make a positive difference. What I wanted to say, yeah, cooperation worldwide is possible, because that's just something that a lot of people don't want to do anything about climate change. Want to say that, it's too, people aren't going to go along with it. People are going to cheat. It's just not going to work. And what this tells us about the ozone layer, this was a global problem. There was, global solution, to stop it or to release less CFCs, and it was effective. So I think this is just a very positive example to get people motivated at climate change, that we've done it before, we can do it again. So this is pretty cool. This is a general infographic about things you can do. Definitely flying is one of the worst things you can do. All the carbon dioxide, hundreds and hundreds of pounds per person to fly a plane, hugely energy intensive. Here's some things you can do in your house. Meat, of course, is a huge thing, not just with methane, but also with CO2. A lot of energy is used to create our food sources. So what I want to do is to make something like this. So right here, go ahead, this is me, say in Long Beach, and go ahead and draw us a infographic showing things you can do, or a totally different scheme. So what's creating the lines in the clouds? What do you think? They are man-made. They're not natural. Can you think? These are actually planes, okay, cutting through the atmosphere, releasing a vapor trail. So this picture just meant to show you there are lots of planes flying. And that equals lots of CO2, which equals a lot of global warming. So, I like to travel a lot. I don't fly a whole lot, but that's just something we have to think about. Is it worth all the traveling we're doing? It creates that global warming. And what radiative foraging components, this is what's holding heat in our atmosphere. So everything on this end of the scale is keeping energy in, like carbon dioxide, methane, nitrous oxides, and water vapor, black carbon on snow, keeps heat in. Down here you see things that are reflecting it, so clouds reflecting it, other sorts of chemical gases. Land use would be places that got desertified, so it turned into deserts, now reflect more sunlight because green from the forest absorbs the light, tan reflects, but just the anthropogenic, this is what's important. This is us, and this is keeping heat in. This is what we need to be focused on. As you can see, first CO2, and then you can make an argument methane. And halocarbons are things like some definite CFCs that are up in the atmosphere that can hold that heat in. So now we're all done with topic 4.